Hello, my name is Santiago Garcia, and today I'll be presenting ambient backscatter. The goal of this paper is to allow devices to communicate and calculate without needing an external battery source. And this is with hopes of realizing a quote-unquote smart dust application. Let's talk about some background. There are a lot of sources of wireless signals, whether that be TV, cellular, or Wi-Fi. Typically, the signals are available all day and all night, and a lot of these signals have very specific encodings. Let's talk a little bit more about these signals. Most of the time, these signals are extremely concentrated in urban areas, think big cities. And prior works have shown that tens to hundreds of microwatts of power can be harvested in these environments. Now, TV towers in specific transmit up to 1 megawatt of power, serving locations up to 100 miles away. Think of receiving your TV in a rural location. Now let's talk about some electrical engineering terms that you should know for the understanding of this paper. To begin, RC circuits stand for resistive capacitive circuits. Basically, any circuit with a resistor or a capacitor in it. And these RC circuits are very popular in many modern electronics. Note that a capacitor does not instantaneously get its charge. It ramps up on a smooth curve and decharges on a smooth curve. And this will be relevant later on when talking about how to actually decode signals in ambient backscatter. Now, an RL circuit is a resistive and inductive circuit, and much like the RC circuit, is used in a variety of applications for electronic components. Now, let's talk about impedance, which is defined as the opposition to alternating current presented by the combined effect of resistance and reactance in a circuit. Now we answered that. What is attenuation? Attenuation is the loss of signal strength in a medium when a wave passes through it. That could be, for example, a network cable or sound going through water. Now, high-pass filters and low-pass filters. Well, an RC and RL circuit can be used to realize both a high-pass and a low-pass filter, respectively. Note that these circuits are not a perfect filter. There is some signal leakage that occurs naturally because of these imperfect components being used in the circuits. Now, let's talk about specifically what is backscattering. We can't do ambient backscattering without understanding what backscattering is. Simply put, backscattering is signal reflection. If you have an antenna, you can change the impedance, and the signals that are received are bounced back or backscattered by an angle that is a function of the impedance difference with the signal itself. Now, let's talk about some of the relevant works at the time of this paper's publication. At the time, tens of microwatts was the standard for energy harvesting via these TV signals. Now, this is good enough for basic sensing and computation, but the power was not nearly enough for communication via, let's say, radio, as radio is a very power-hungry thing to do. Now, that leads us to the main challenge of this goal that the authors had. Communications of any kind are extremely expensive. So the authors wanted to answer, how can we communicate without using traditional means? In particular, in a energy harvested in lower power setting. Their solution, this paper introduces ambient backscatter. So instead of generating signals on their own via a device, the authors decided to use existing signals to communicate between devices. Now, this has the great realization of only requiring about 5% of the harvested power total to communicate via two devices. That means there's a whole 95% of harvested power that can be used for other calculations. Now, there are some challenges associated with this solution. And before I get into those, I'm going to talk about how ambient backscatter is a little different to a method of, let's say, RFID readers. For instance, RFID readers work by having a reader and a tag. The reader sends a constant signal, which is not only regulated by the reader, but when the tag receives power, the wave that is coming into the tag is 100 or more microwatts. And additionally, the RFID reader coordinates the actions produced by the tag. There's a central authority. Unlike this, ambient backscatter uses uncontrollable signals from other devices, let's say a TV tower or a radio tower, and receives only about a half of a microwatt of power. Again, go back to the previous slides talking about how 10 microwatts is not really a whole lot of power to be able to do any kind of meaningful communication with. Additionally, even if you have a communication protocol, you still need a media access control protocol to communicate effectively between two devices without stomping on top of each other. In addition to this, decoding any signals without the use of a battery and expensive power-hungry hardware like an ADC are extremely complicated. So, now that we talked about some of the problems to reach that goal, let's talk about some of the solutions that the authors proposed in their paper. To begin, how do we extract backscattered signals? All of the backscattering devices that the authors designed obtain and see signals from an outside source, whether that be a radio tower or a TV tower. Now, they can control these signals, and there's also the additional problem of these signals being analog. Now, if it was a digital signal, it would make averaging an easy task, which through averaging, they can create a weak reflection and through that communicate with other devices. Now, if they use the same weak reflection, they can change the average amplitude, and a receiving device can track these changes to see a bit stream. But again, the issue still is, how can one do this without using a power-hungry analog to digital converter? Let's talk about extracting information from backscatter. Wideband TV signals change at a much faster rate than our ambient backscattering signals. Therefore, backscattered signals can be correlated together by taking multiple samples and seeing that slower change in signal. Backscattering a signal also adds complex attenuation to the signal, which can then be used with the multiple samples to track whether or not a 1 or a 0 is being transmitted. Now, the actual math behind this uses Nyquist rates and a combination of the backscattered signals and the wide band TV signals. And I'll leave the proof up to the reader or listener to go and understand via the paper. So let's talk about the transmitter design of this ambient backscatter device. Again, to reiterate, traditional backscatter is achieved by changing the impedance of an antenna. And through the difference in impedance of an antenna and a signal will be backscattered at a specific angle. Now, the transmitter design for this ambient backscatter uses a switch that can actually change the impedance of the antenna that they're using. And through this change in impedance, the backscattering signal can be used to represent either a 1 or a 0 by a receiver. Note that the topology of an antenna has to be optimized for the specific signal that they are using in order to have highly efficient communication between these two devices. So, Speaking of transmission, let's talk about how a receiver works. How do you decode on a batteryless device? RC circuits here come to the rescue. As a reminder, RC circuits stand for resistive capacitor circuits, and that uses a resistor and a capacitor. A little bit of background on these circuits is that a capacitor will slowly charge and slowly discharge when applying a voltage. This provides a cheap way to communicate an average to another device. And additionally, by picking the right values for the said RC circuit, an end user can selectively filter out frequencies that are not needed. For example, high TV frequencies. And we'll see later why this is important. Let's talk about the specific receiver design. Again, TV and cellular signals encode information at a mixed rate. The signals vary. And backscattering transmission was realized to be performed at a slower rate so as to not be confused with the TV or cellular encoded signals. Now, in order to actually design this, the authors used a receiver broken into 3 circuits. An average envelope, which was realized with an envelope detector, which in all cases is just a peak detector, and an RC circuit, which acts as a filter to average out any natural variations that can occur in the signal. The next part of the receiver is a compute and threshold circuit, which takes the output of the previous circuit, and that could be a 1 or a 0, and then computes a threshold value of those 2 values, and then after that, it's shoved into the last part of the receiver, which is a comparator, which will take the threshold value that is calculated in the compute threshold circuit and the value from the average envelope and compare the 2 values and output whether a received signal is a 1 or a 0. Now, this eliminates the need for a ADC that's very power hungry, and all this hardware is analog, so it doesn't require any extra power to actually act. So, now that we've talked about the transmission and the receiver, let's talk about how the authors used a distributed media access control protocol for these battery-free devices. So the authors used a carrier sense protocol. Multiple access is talked about later in the paper. Unfortunately, these battery-free devices, again, like previously stated, can't detect energy levels. They do not. That requires a power-hungry ADC that just is not feasible in a power harvesting situation. So, question is, how does a battery-free device detect energy without access to the actual energy levels? Well, again, the authors decided to leverage hardware for energy detection. These RC circuits are back to help. These circuits act like a high-frequency filter. So, with no backscatter, the output's either all 1s or all 0s. But with backscatter, these transitions occur between 1s and 0s all the time. Now, using these transitions as a proxy, the authors were able to perform energy detection. And I'll leave you the math to look at in the actual paper itself. Now, let's talk about the actual protocol design. This protocol was broken into 2 parts, a physical layer part and a link layer part. Now, due to the nature of backscattering signals, there is a potential that lowering or raising a power level could lead to a 1 being seen as an increase or decrease in power, as opposed to the typical increase of power representing a 1. Now, their solution to this is using a FM0 encoding in the physical layer. Now, an FM0 encoding takes the bits that it receives and encodes them into 2 symbols and encodes this information using a symbol transmission, effectively making the bit encoding not necessarily related to the power level, but to the transitions in the power. So that means a 1 can be represented by a decrease or increase in power, and a 0 is represented by nothing happening in the power. The next part of this protocol is the link layer. And the link layer uses a basic packet structure. Now, I'm going to describe some of what the packet contains. It includes a bit stream to wake up digital hardware, so just ones and zeros, and this is about 8 bits, and that was deemed enough to effectively wake up the digital hardware for receiving. Follow that is a preamble, which is then followed by a header, and this header is broken into a data type, a destination address, a source address, and a CRC check for the header itself. Then comes the data, and finally a CRC check for the whole body of the packet. And this is a very basic packet design that you'd see in a basic network protocol. Now that we've talked about the design, the proposed design, let's talk about some further additions that the authors proposed. So the current prototype that they designed can only be ran at 1 bit rate, but the authors proposed that future designs and future devices should be able to run at different bit rates, and they could do this by using a demodulator for each of the rates. Now, like previously stated, their immediate access control protocol only has the carrier sense function, but further work would work on designing collision avoidance mechanisms for these low power environments, and this would be hopefully work to lower the amount of collisions that happen between communications of devices if there's a lot of devices. Now, just like the collision avoidance, future implementations could also use RTS-CTS mechanisms to handle the hidden terminal problem, preventing nodes from transmitting for a fixed amount of time, just like you would see in a network sense with wireless routers in a busy environment. Now that we talked about some further additions the author proposed, let's actually see the meat and potatoes. On your right here, you'll actually see the Ambient backscatter device. And as you can see, it has an antenna, and on the board itself, it has both a transmitter and a receiver built with those analog circuits I talked about earlier. There are 2 LEDs and 3 touch sensors, as you see on the bottom of the board, in A, B, and C. And you'll see that these are used for an application later in this presentation. So, the authors created this prototype, which is battery-free, can harvest power, and backscatters TV signals at 539 megahertz, which is typically what TV towers in America use. And then this is connected to an MSP430, which performs any computations that this ambient backscatter device needs. Now, let's talk about some of the tested locations they did with their prototype. They tested it in both indoor and outdoor settings, and this was in the Seattle, Washington area, which, in case no one has been there, is a very urbanly dense area. And they are using or borrowing a 1 megawatt TV tower that is transmitting at 539 megahertz. I say borrowing because they're not actually owning the TV tower, they're just using the signal from the TV tower. And this was tested with distances up to 10.5 kilometers away from the actual TV tower. Now, let's talk about some of the results of the testing. They were able to achieve about 3/4 to 3.5 feet of distance between the devices before the bit error rate was way too high to effectively transmit data between 2 of the devices. Now, this is different than the actual distance from the device itself to the TV tower. This is the distance between the 2 devices that are transmitting to each other. Now, outdoor environments were seen to perform better than the indoor environments, and they chalked this up to being due to signal attenuation that occurs when a signal goes into a room or goes through a building, and it will lower in power. Now, their carrier sense protocol detected the presence or the absence of a backscattering transmitter with a 99% success rate, which is really good for a small embedded device. Now, the authors also included a couple of proof of concept applications. First one is a smart card. These devices can legitimately communicate mostly anywhere that there is a TV signal or a radio signal or some kind of Wi-Fi signal without needing any kind of reader like an RFID tag and reader setup. So by using this ambient backscatter device, smart cards can be realized and they can be used for payments or as a digital pin pad to transfer content. Now, the authors themselves were able to prove this by transmitting a hello world message using the touchpads on the prototype. Now, let's say they touched the A pad. This would send a signal using ambient backscatter to another of the ambient backscatter devices, which would then print a hello world message via an LED. In addition to this smart card application, the authors also proposed a grocery store / warehouse item tracking system. By attaching these items or by attaching these ambient backscatter devices to items on shelves, each of the devices could broadcast an ID occasionally, which would then allow other devices in that area to check if they are out of place on a shelf or in a warehouse. Now, when this prototype was used in practice, it only took about 20 seconds to flash an LED to symbolize an item was out of place. Now, I personally can see that there are a lot more proof of concept applications than just the two that they've proposed. And I'd love to see where this paper goes in the future. That being said, thank you for listening, and I hope that this paper presentation taught you something about the ambient backscatter research. Thank you.